from Philadelphia, so from Temple University. So she will tell us about wave propagation on cosmic string spacetimes. Whenever you're ready. Thank you.
Great. Thank you for the introduction. I hope everyone had a good first day at the conference. I was disappointed not to be able to be there in person, and grateful to the organizers and the Fields Institute for changing the mode of the talk for today. So I'm going to discuss some work which is joint with Jared Wunsch from Northwestern University. And we're interested in understanding the wave equation on a class of spacetimes which we call cosmic string spacetimes. And so what are these cosmic strings? Well, in 1976, a physicist, Thomas Kibble, theorized the existence of some topological defects that may have formed in the very early universe. So when I say very early universe, I sort of mean the first sort of nanoseconds. And these are sort of theoretical objects that may or may not exist out there, which are a time-like one-dimensional topological defect due to symmetry breaking during a phase transition. So kind of roughly, the idea is analogous to, say, when water freezes and forms ice, you see in your ice cubes little air bubbles, and this happens because there's asymmetries in the formation of the lattice structure, right? Freezes in different places, lattice structures form in different places, they lock up, they come together, there's an asymmetry and sort of have to close and form an air bubble. And some sort of analogous process is believed to have possibly occurred in the early universe. And so this one-dimensional defect is the string. And here, the defect is this time-like one-dimensional object at r equals 0. And this string, I should say, is separate from the string of string theory, and kind of has its own place in the physics literature. And it's of interest to physicists who are kind of actively exploring to see if something like this is really out there, partially because it may explain some things related to like matter distribution in the universe. But also apparently in recent years, there has been some potential connection between this string and the ideas in string theory. But I come at all of this from the mathematics perspective. And so for me as a mathematician, I kind of come in with this work from the physicists Jaku and 't Hooft. And so here they were able to write down an explicit metric in 2 + 1 dimensions. So I perhaps should redraw my picture. Where r equals 0, we have this so-called string. And here A shows up as a constant, which is proportional to the angular momentum of this one-dimensional object. And in their work, there is, I mean, you can ask why is this 2 + 1 dimensions? There are some benefits to it, but they start with 3 dimensions and kind of 3 spatial dimensions and quotient out the third using some symmetries. And so we focus on this 2-dimensional picture. And so I sort of come at this with the understanding that these cosmic strings are of interest to the physicists out there, but I'm really sort of looking at this geometric object, given this metric from Jaku and 't Hooft, and what can we sort of understand about it, and what can we say about waves in this context. And so one thing to note is that if A equals 0, so if there's no angular momentum, of course, we have a much simpler object. And in fact, this would end up being something where the t equals constant slices are 2-dimensional cones, something that is much better understood. So we're really interested specifically in rotating cosmic strings. So this case where A is positive. And we can note that while there is something interesting happening owing to this topological defect, if we can see sort of simply by making a change of coordinates with t prime equals t minus a phi, that this reduces our cosmic string metric reduces to the flat Minkowski metric in polar coordinates. And so locally we have something flat, although globally there's some interesting things going on. And in particular, we see some sort of strange causal behavior, which you can note if you by considering the closed curves where we just take t and r are constant. So here we just have our closed circle. And so then, of course, if we look at a tangent vector, this is pointing in the angular direction, and we can ask ourselves, well, what is the size of this tangent vector as measured by our metric? Well, we see that we have r squared minus a squared. And notably, this changes sign depending on the value of r. And if r is small, so if we're close enough to the string, then we have that the size of this vector is negative, and so this is time-like a curve with time-like tangent vector. And so we see the existence of these closed time-like curves, which sort of tell us that there's something sort of strange going on here. In particular, these rotating cosmic string spacetimes are not globally hyperbolic, so I can't find a Cauchy hypersurface where every time-like curve intersects the hypersurface exactly once, because of course we have these elements close to the string. And so in particular, that makes studying the wave equation a little bit challenging. And so there are sort of a few things that we can think about right off the bat of like what makes looking at the wave equation tricky, and sort of say what we're going to do instead. And so we have our metric, and we can write down our wave operator using just sort of a simple direct calculation, where our wave operator is just the D'Alembert. I've written this in a sort of compact form, but here we'll note that at top order, if we look at our second order term here, of course, this just comes with the constant coefficient 1, whereas this term right here does have this coefficient r to the minus 2. This is notable since that means that it has a coefficient that blows up as we get close to this singularity at r equals 0. And that is going to be relevant to our analysis as we proceed. And so thinking about what we might be able to say or not about waves on cosmic string spacetimes, the first challenge is that it's unclear how to set up a Cauchy problem, because of course, if we are not globally hyperbolic, we don't have a Cauchy hypersurface, so we don't have a place to put our initial data. What does it mean to have initial data somewhere where there's some closed time-like curve, something that intersects the hypersurface more than once? It would have to be somehow data time 0 and some future time as well. But that's simple enough. There's no reason why we have to study the Cauchy problem. We can study the forcing problem instead. And so thinking of this as just understanding existence of solutions to our forcing problem. And then of course, Duhamel's principle tells us that there's some, in some picture, we can think of these as very similar setups. Rather than inserting some initial data, we're kind of just inserting some sort of experimental force. The other observation is that we can look at the conserved energy, which is associated with our Killing vector field partial T. This is a stationary spacetime, so of course we have this conserved energy quantity, but we note that in our integrand we have this 1 minus r squared over a squared, which changes sign depending on the value of r. And so we have this unsigned integrand, which means that our usual energy methods aren't available to say that there's existence of solutions to our wave equation here. And the idea is to sort of take a different approach that allows us to get a different sort of microlocal version of an energy estimate, meaning another approach to get some L2 based bounds that allow us to proceed in sort of a similar fashion as we might hope if we had access to traditional energy methods. And so this will be done in the spirit of Doorster-Motte and Hormander's Fourier integral operators 2 paper, using propagation of singularities. And so I'll sort of finish out this introduction by kind of actually stating our main theorem. And we will then sort of exit the cosmic string picture and focus on kind of understanding what the spirit of this paper is and how that's going to inform this current work. So another thing to note is the thing about kind of the possibility of forward in time solutions. So one might hope that if you have F with some sort of compact support, that when you look for your solution U, that this is going to live in some sort of forward in time flow out of my support of F. But in this case, we actually can't get it here. And we saw this when we first started looking at this problem, looking at the mode by mode picture. So in that case, we end up with an operator which is of Jacobi type. So it's elliptic in some areas and hyperbolic in others. And what we see is that, so it's elliptic near the string, and therefore by unique continuation, we can't have this picture. We can't have a solution U that is supported only in some t greater than t naught for any arbitrary t naught. So that's maybe a bit disappointing in the sense that you would sort of hope to be able to get this picture when you're looking at the forcing problem. And so it would just adapt a slightly different strategy that does allow some sense of forward in time solution by focusing at where the singularities are rather than looking at where the support is. And so the main result is a statement on this existence of solutions to the wave equation on our cosmic string spacetimes with the rotating string. And I will simply say let F be sufficiently nice, make it smooth if you'd like. And if we have a compact set K, then we can solve there exists a solution on the interior of K. So we say we have some almost global solutions in the sense that this can be an arbitrarily large compact set, but we do need some compact set. And we're able to make some sense of U as a forward in time solution using the concept of wavefront set. And so as I said, we're kind of interested in understanding where this singularities are, and wavefront set is what lets us do this. And I will note that as I've stated it here, is not the sort of complete statement from our paper. And in fact, our full theorem allows for a larger class of first order perturbations that also includes Klein-Gordon. And so we're going to sort of exit the cosmic string picture for a minute and talking about the pre-existing theory, looking at this with Droster-Motte and Hormander picture for smooth manifolds. So I'm trying to be consistent in my notation here, and CS was used for our cosmic string metric, and I will use G when we're just looking at these general smooth manifolds. And so throughout, just let XG be a smooth Lorentzian manifold without boundary. And then we, of course, can write our wave operator as the Dal version. We're here. Oops. This is the absolute value of the determinant of the metric. Right, and so our focus is kind of on understanding singularities. I mentioned propagation of singularities, and this would be relevant to our understanding of a forward in time solution. So here singularities are measured via wavefront set. This is something that lives in the cotangent bundle of our manifold, and roughly the wavefront set tells us where and in what direction a function lacks differentiability. And we can give sort of a definition by example, where if we have this sort of two-dimensional heaviside function, so here if the x-axis is tangent to the screen, and the y-axis is coming out towards myself and towards the audience, we have something that looks like this. And if we want to know where the wavefront set is, well, we're looking where and what direction we lack differentiability. And of course, anywhere away from x equals 0, we are just constant. And so the issues are at when x equals 0 and when we move in a transverse direction. And we can record this with our wavefront set and our cotangent bundle, which is when x is 0, and we don't have this y component, and we have we are moving transversely in the y direction, and of course any value of y. And so that's perhaps a definition by example. It's the most useful for kind of having a picture of what this means intuitively. But formally, it's much more helpful to have a definition using pseudo-differential operators, which I will just state briefly. Where if we have a point in our cotangent bundle, we say that it is outside the wavefront set. So we usually define the wavefront set by its complement, that we are outside the wavefront set if there is some pseudo-differential operator B, which we can think of as being sort of microlocally supported at this point Q, such that B phi is smooth. And when we talk about propagation of singularities, the key is these null by characteristics. And we can think of null by characteristics as being lifts of geodesics to the cotangent bundle, or more specifically, they are the integral curves of the Hamiltonian vector field within the characteristic set of the principal symbol of the wave operator box G. So again, our kind of intuitive definition is simply thinking of these as lifts of the geodesics, but certainly we'll want to have our formal definition as we do some calculations later. And sort of the most basic form of the propagation or singularity statement is simply that if we have a box GU as some smooth function, that singularities propagate along these null by characteristics. And so that is to say that given a null by characteristic, that is either contained entirely in or entirely outside of the wavefront set. And this statement can be given in terms of estimates in a form as we have here, where we can think of some region gamma in the characteristic set in our cotangent bundle, and C is going to be supported in this region. And then think about the flow out under the null by characteristic flow, and sort of collect the points that you end up at. And this is a region beta, which is where B is supported. And so our assumption that F is smooth is really just so that we sort of already have guaranteed that we have control over this term. And so the propagation of singularities is simply saying that if there is no wavefront set here, meaning this thing is finite, then there's no wave set here, because we have control over the left-hand side. A lot of sources on this always they call it propagation of singularities and then quickly point out that it really ought to be called propagation of regularity, since really what we're saying is that if we have regularity here, then we have regularity forward under the flow. And it is just sort of a standard truth that in these estimates, there's sort of this cost of this remainder term. But the kind of good news is we can measure U in as sort of as bad a space as we want. So we're sort of able to get control on the right-hand side there. And so in the Fourier integral operators 2 paper, I referenced this propagation of singularities result is key in obtaining statement on existence of solutions to box G U equals F. They're not specifically looking at the wave operator, but look at a larger class of operators, and the wave operator falls under that picture. And so in this case, if assuming that there is some compact set K such that every null-black characteristic over K eventually leaves that compact set. And it follows that there exists a finite dimensional space N such that for any F with some order of Sobolev regularity that is orthogonal to N, then I can find U with one order more Sobolev regularity such that box G equals F on the interior of my compact set. And so the idea of the proof is that we start with this propagation of singularity statement with in this sort of estimate form, and we're saying we have some region K, where if I look at any null bicharacteristic over K, it eventually leaves. And we can kind of piece together some estimates and use some clever functional analysis. So in particular, if the support of phi is contained in K, well, what we can do is sort of piece together some estimates by looking at sort of phi times, with some operator applied to it supported in different regions in our cotangent bundle, where we say, well, there's sort of two options, right? If we look at any point over K, either we're in the characteristic set or we're out of it. In the case that you're out of the characteristic set, we have access to a kind of microlocal version of elliptic regularity, which generates a similar kind of estimate. And if you're inside the characteristic set, well, then think about the null bicharacteristic that goes through that point, and it has to leave K. That's the assumption of the theorem. And well, if it leaves K, I know I can sort of put my region gamma out here, choose my region beta to include that point there. And not only do I have control over this, but if phi is supported inside K, then this is in fact 0. And so when I have something that is supported inside K, we can get a simplified estimate that loses that first term on the right-hand side. And then we can sort of add these all over together and drop the B. And use propagation of singularities to show that, so if we have a compactly supported distribution, we get this estimate, which we can think of as sort of a microlocal energy estimate, this L2 based estimate, which again comes at the cost with this remainder term. And the key observation here is that HS plus 1 embeds compactly in this H minus N. And so if we let N denote the null space of box G, which turns out to be finite dimensional, a compactness argument ultimately yields that if we, in addition, assume that phi is orthogonal to the null space, then we can further simplify this estimate and drop this remainder term. And it's crucial here that we have this compact embedding because it allows us to construct an argument that says that if we don't have this, we would end up with something that would have to be in the null space. And then I'll just sort of briefly go through the idea of how this helps us and what the role of this energy estimate is. And for simplicity, we'll just assume that box G is self-adjoint. And so if we assume that F is orthogonal to this finite dimensional space and has some level of Sokolov regularity, we can define this linear functional T on the image of some compactly supported Sokolov space. And at first glance, it may look sort of like this is cheating, where the whole question is, do solutions to this exist? And here we're somehow trying to like invert our operator. But the point is, because we're looking at orthogonal to the null space, in fact, this is well defined even if you have, say, two different functions which get sent to the same output by box G. So we're originally able to define this on a subspace without having to know that box G is convertible. And then we can use this energy estimate 1 to get a bound on our linear functional. And so then we have access to Hahn-Banach to extend where this is defined, and then use Riesz representation theorem to say that there exists a U in H minus S such that our T applied to any element of HS equals to this pairing. And putting that all together, we see that T box G phi on the one hand is equal to phi paired with F, but on the other hand is equal to box G phi paired with U, and we made our lives easy by assuming box G is self-adjoint. And so of course, this tells us that box G U equals F distributionally. And so again, kind of the takeaway is the utility of this estimate, which we're able to obtain using propagation of singularities and some functional analysis owing to this compact embedding from the left-hand side space into the remainder space over here in our original estimate. And so that's kind of the flavor of the background theory that we want to exploit when studying cosmic strings. That we say, well, this doesn't require, or this isn't necessarily limited by some of the strange features of our geometry. There are certainly questions that we have to ask and things that we have to look at and try to understand better. And so in the last about 20 minutes of my talk, we'll return to this cosmic string picture. And so right in we said it in the first section that in this cosmic string picture, we have our space-time given by this metric and our wave operator here. And I will remind us again the importance or the existence of this term where we have this vector field which comes with this r to the minus 2 factor, which blows up as we get close to the string. And we're just looking for existence of solutions. And given that we are hoping to utilize propagation of singularity estimates, and that tells us that singularities propagate along null-by characteristics, naturally we want to understand the null-by characteristics on our spacetime. And so using our dual variables here, t tau x with xi and phi with eta, we see our principal symbol given by this expression here. Essentially just sort of taking to top order what's happening from our wave operator. And that yields our Hamiltonian vector field, which maybe in total is a lot to take in all at once. but we'll be focusing on different pieces of it. And then of course we have our characteristic set, which is where our principal symbol is 0. And we'll kind of have two different cases that we think about. First, when a tau plus eta is 0, well, we see that things simplify quite a bit, right? We don't have this, we don't have this, we don't have this, we don't have this. And so we're just left with two terms in our Hamiltonian vector field, and a simplified characteristic set as well. And we'll also look at the case where a tau plus eta is non-zero, but we'll focus sort of specifically on just a couple pieces, particularly what's happening with R and Xi, and just as a note on the time component. All right, so taking those simplifications for case 1, where a tau plus eta is 0, perhaps I should go back and emphasize that in all cases, tau dot and eta dot are 0, so these are constant. And so owing to these simplified equations, we have our null characteristics are fairly straightforward to look at, right? Phi, tau, Xi, and eta are all constant. And we have these expressions for T dot and R dot, which are just equal to constants. And so the first thing we note is that when we look at how R changes in time, well, we have tau over Xi, negative tau over Xi, but on our characteristic set, tau is equal to plus or minus Xi. So drdt is just plus or minus 1. So regardless of the null characteristic, we always have that we're either uniformly increasing in R or decreasing in R as T increases. So we have either incoming rays or outgoing rays. We also see that T is monotone as tau is constant, and we have a very simple form for R. And we note that depending on whatever our initial conditions are for Xi and R, we can always find some value for the curve parameter so that R of S is 0. So in fact, these null characteristics will reach R equals 0 and will interact with the string. In the case that a tau plus eta is non-zero, we don't get these simplifications. But we can sort of focus on this coupled equation for Xi dot and R dot, and you can just do this out by hand, plug it into to something, and see this expression for R. And notably, right, we have a tau plus eta is constant, so this is and non-negative. I'm sorry, and non-zero. And so we have a strictly positive term and a non-negative term. And so R of S is never 0. And so these do not interact with the string. These never see the string. But they do have some sort of strange behavior where T dot, this expression right here, the sign depends on R, right? We have tau and eta are constant, but the sign will change with R. And so the curve, the null characteristic is not monotone in time. It somehow is sort of moving forward and backward in time, depending on where you are along the curve. That's one of the things that makes maybe talking about forward or backward in time solutions tricky, but there is sort of a helpful feature here that we see as we move along the curve. Well, R always eventually goes off to infinity for large S, positive or negative, and then this term, eventually, this sort of wins out. And so we'll eventually have the same sign as tau asymptotically. So while the null characteristic itself may do some sort of funky things in time, moving forward and backwards, it is asymptotically either a forward in time null characteristic or a backward in time null characteristic. Which allows us to still sort of think about this thing as either being a forward in time or backward, or forward or backward in time. So the point is that we have sort of two scenarios. Either the nullby characteristic does not interact with the string, in which case it's maybe not generally monotone in time, but it is eventually monotone in time, and it moves out towards spatial infinity. And then the other option is that it does interact with the string at r equals 0, but these are much simpler, right? These are, excuse me, monotone in time along the flow and are either incoming or outgoing. And so where does this leave us in terms of the picture of the sort of theory that we were looking to exploit and understand? Well, the nullby characteristics that do not interact with the string, the theory applies, right? As far as those nullby characteristics are concerned, we live on a smooth manifold without the boundary. And so there we can use our standard propagation of singularities result. And the work that needs to be done is by understanding sort of what happens here and trying to obtain an estimate using that shows propagation, what happens with propagation at the string. And so in order to study this interaction with the string itself, it's helpful to do something called blowing up the singularity. And so very, very roughly, as you know, I can describe in under a minute, the idea is to sort of think of working in polar coordinates as we've been doing as a way to sort of distinguish what's happening at the singularity, right? So working in polar coordinates, I'm able to distinguish points at r equals 0 depending on what angle you're entering from. And so r equals 0, sort of coming from one angle is somehow different than coming at this different angle. And the end result is creating a boundary, a cylindrical boundary at r equals 0. And you can sort of do this formally using kind of blow up and blow down maps that go in between this blown up picture and the original. But the rough idea is just sort of thinking of this as polar coordinates that allow us to distinguish coming in from different angles. So now if we look at this blown up space-time, so let X be this blown up manifold, X becomes a manifold with boundary, where the boundary is this cylinder at r equals 0. And the boundary is equipped with a boundary vibration, which is compatible with the metric. And the fibers of this are going to be integral curves of a partial t plus partial phi. And so what do those integral curves look like? Well, they're going to be these sort of helical structures going up the cylinder. And I'll say maybe a couple words about the significance of this. So one thing is, as I have tried to point out, we have this vector field showing up in our wave operator coming with this r to the -2 factor. And so this is our very, very singular part of our wave operator. And so we are going to need to sort of study what's happening there in a different way. Another element that I am not going to get into in detail in the talk, but is maybe worth mentioning, is that because we have are working on this manifold with boundary, our sort of normal pseudo-differential calculus is sort of not amenable to this study. And so we use what's known as the B pseudo-differential calculus, Melros's B pseudo-differential calculus, which works with vector fields which are tangent to the boundary, and therefore is more equipped for dealing with the boundary that we've created. Unfortunately, the wave operator itself does not lie in the pseudo-differential calculus, and in fact, it lies in a different edge calculus. And so when working with these objects, we sort of end up with this vibration coming from the integral curves of this in the edge structure of our manifold. And so being able to sort of think about this vibration is useful in coming up with sort of understanding how these different pieces work together. All right, so sort of in its simplest form, we have a propagation statement or what happens at the string, and we're saying that if the wave operator on our cosmic string spacetime applied to you is 0, then in this case, if there's no wavefront set coming into a given fiber, there's no wavefront set outgoing from that fiber. So again, the nullby characteristics that interact with the string, we have incoming rays and outgoing rays. And so if we have an incoming ray into this fiber with no wavefront set, then all of the outgoing ones have no wavefront set. But notably, sort of conversely, if they're when you do have wavefront set coming out of the fiber, it suggests that you can have the whole fiber sort of gets excited, and so somehow you're having information propagating all along this fiber, which includes both forward and backward in time, as if somehow the string is able to sort of communicate with what's happening backward in time, with information propagating out of it. Now, obviously, the statement that we can't assume the absence of wave.
Sorry. Can you say that again? I didn't quite get it.
Yeah. So we yes. So we can't say that there is absence of wavefront set. Sorry, let me rephrase that. If there is wavefront set coming into a given fiber, it could excite the entire fiber. That is a possibility that we see. Like, we can't rule out that possibility. That is not the same thing as guaranteeing that it excites the entire fiber, but it looks like it's possible. And if it is possible, then that would suggest that there's this very strange, like, backward in time communication.
Okay, thank you.
Yeah, thank you. So roughly the idea of the proof is to use a positive commutator argument where you have a given pseudo-differential operator f that we want to write this commutator with our wave operator. We're here kind of we want this piece to be something which is sort of supported on the incoming rays. So this kind of sees the incoming rays. This backwards. Do have it backwards. So this should be on the outgoing rays. This is supported on our incoming rays. Then you have a piece that's elliptic and a remainder term. And this is sort of a standard structure of argument for propagation of singularities, where we sort of work on the symbol side, and the idea is that somehow these null characteristics are kind of the key structure that allows you to write this commutator in this kind of form in terms of where the support is for your operators B and C. And once you have your positive commutator, you are able to write something in this form where you relate the side to the commutator applied to U paired with U, and assuming the box CSU is 0, you then are able to obtain an estimate of this form when we see something that looks like our propagation of singularities estimate. Where here we're saying if there's no wavefront set on the incoming ray, then there's no wavefront set outgoing from that ray. And you can sort of see the significance of the fibers because what happens is when we're looking at sort of this general form of what the commutator looks like, well, when we commute anything with box CS, we end up with, you have to include these terms that have this a partial t plus partial b together with this r to the minus 2 factor. And that's big. It's huge. It's huge near the string. And the only way to deal with it is to kind of look at things which are invariant on the fiber. But if we're restricting to pseudo-differential operators, which are invariant on the fiber, they don't really differentiate between different points. And so that's why we kind of have to think about things that kind of contain that entire sort of helical structure. So another thing to note is when we went through the sort of existing theory for smooth manifolds, I said that there was kind of this key thing where we end up with this estimate form of the propagation of singularities, and you can be a little clever and get rid of one term, and then there's the fact that one term on the right-hand side, and then there's the fact that you have this compact embedding. And well, for us, we end up with something that has that same kind of form as what I showed earlier, but we have some sort of funky spaces where X embeds in Z, but not compactly. And this is owing to what I was speaking of before, that since we have a manifold with boundary, we're using this B pseudo-differential calculus, but that actually doesn't play very well with our wave operator. And so we have this sort of like mix of calci that we need to use. And so we end up with these sort of weighted B-Sobolev spaces, and the weights on this space and this space don't match, and you end up with something that does not have this compact embedding, which really is essential for that argument. But the saving grace is the observation that we have this lower bound on that A partial T plus partial phi squared vector field applied to U. And ultimately that allows us to exchange derivatives for decay and obtain another estimate, and then interpolating between this and that other estimate ends up with something where we do have that necessary compact embedding. And so finally, I can make a little more sense of this claim that our solutions are the solutions that we know exist are forward in time, and that is to say that so we have this almost global existence of solutions, and that the wavefront set of the solution is contained in this asymptotically forward in time flow out of the wavefront set of the forcing term together with the string itself. And so again, that's where the observation that these that while the null-byte characteristics may not be everywhere monotone in time, they're asymptotically monotone in time comes into play. But we can at least talk about these asymptotically forward in time flow outs. And while we can't say anything about the supportive view, we can say something about the location of the singularities as measured by wavefront set. And I'll leave it there. Thank you.
Thank you very much, Katrina. Maybe do you have any questions?
I have two questions. Can you hear me?
Yes.
Okay. The first question is, so you look at the forcing problem, and another option perhaps would be to look at the scattering problem. I think to remember some old paper of Alain Bachelot where he does this for this kind of model. Can this work with your approach? So somehow to characterize some scattering data, we can solve this equation in spite of this time-like closed geodesics.
Yeah, so I don't know the answer to the question. I don't know if it will work or not. I am familiar with the Bachelot paper, which we certainly looked at, and it's very helpful.
Yeah.
He has a different setup where he sort of has some cutoff in the metric, which sort of doesn't see some of the worst of what's going on at the string. And so while he does allow for some sort of abnormal causal behavior, you don't see this this interaction at the string. So I don't, and I have not looked at what that would do to the scattering, but I do know the paper you're referring to, and that would be an interesting thing to look at.
And I have a second question, perhaps I'm wrong, but it looks a little bit like the time machine in block 3 of Kerr. Is this similar, and did you look at that?
That I don't know. I did not look at that. This may be an interesting thing I should look at. You're saying it looks similar to...
I think you have this closed time-like curves also just because the integral flow of d phi is becoming time-like in block 3 of Kerr, and I think this would be an interesting problem to look at with your techniques.
Interesting.
Yeah.
Well, thank you for that.
Any other questions? Okay, maybe I can ask something. So you said that you're looking at rotating strings because there would be a lot of simplifications if A is 0. But in the proof, it sort of seemed like everything was that there wouldn't be a substantial simplification for A equals to 0. So I'm wondering if you could elaborate on that. Is it that the helicoidal thing is not
Yeah,
there if A is 0?
yeah, exactly. So you would sort of get this, I mean, the sort of interesting or challenging vector field here just becomes
Mhm.
completely different if you don't have A.
And does it change the theorem you showed us earlier, the theorem of and the comment that you had made earlier about does that
Um,
change if it's 0?
so yeah, you have something different about, because then you'd be looking at propagation of singularities. Like if you wanted to use these techniques, you'd be looking at propagation of singularities at a cone point, which I believe there is work with Wunsch and Vashi that establishes sort of what would be needed there, where you get diffraction at r equals 0. So I think you would still get something that's not, I mean, you still have things that are interacting. Like you wouldn't be able to just appeal to the Doistermaat-Hormander picture, but
Mhm.
there is existing work out there that has sort of what you need.
Okay, thank you. Okay, if there's no more questions, then maybe let's thank Katrina again. And with this, we wrap up the session today, and I guess I'll see you all tomorrow at 9:15. Thanks a lot.
Thank you.
See you. Bye.
Bye.